Good morning, everybody. For the few of you who don't know who I am, my name's Peter Fisk. I'm Chief Executive of the National Measurement Institute. Thank you all for coming this morning, and I'd like to welcome you all on behalf of the traditional owners of the land on which we're meeting today, and I'd also like to pay my respects to their elders, both past and present. We're here today to listen to a talk by Dr. Terry Quinn, Emeritus Director of the International Bureau of Weights and Measures. Terry started his career in the National Physical Laboratory in London in 1962, and between 1962 and 1967 he did a number of things, including developing an instrument known as the cryogenic radiometer, which essentially links optical power measurements to the electrical units. He also became involved in mass measurement and also in the determination of the fundamental constants, which of course leads in part to his interest in the redefinition of the international system of units. From 1978 to 2003, he had the honour of being the director of the International Bureau of Weights and Measures, and I believe he was the second longest serving director of that organisation, which is a remarkable achievement. He retired from that position in 2003, and since then he has been active in the field of measurement, supporting various BIPM committees, and taken a particular interest in the CCU for the consultative committees of Committee for the Units of Measurement. He was elected a Fellow of the Royal Society of London in 2002 and was honoured with a Commander of the British Empire Award, or CBE, by the Crown, I believe, in 2004. So a very distinguished career which still continues to this day. I thought I would share with you an anecdote of my first meeting with Terry. In 1993, I was a junior scientist just recently appointed to the National Measurement Laboratory here, and I was sent to attend what was then a meeting of the Committee for the Definition of the Second, now the Consultative Committee for Time and Frequency. And so I arrived in Paris on my first overseas trip and thought I knew how to get to BIPM, but I walked up the road and failed to turn right up the path that led to BIPM, and I ended up at the top of the hill in the Parc de Saint-Cloud, which is a large public park. And when I got into that park, I could then look down the hill and I could see the BIPM, and I realised where I was and the mistake that I'd made. But I was also running a little bit late, and I didn't want to distinguish myself by being late for my very first meeting at BIPM. So I thought there might be a back gate, so I came down the hill and found that there wasn't, in fact, a back gate. In fact, there was a high fence. But having had many years of rock climbing and other things in my past, this wasn't too much of an obstacle. There happened to be a tree on either side of the fence, so I ascended the tree and then transferred to another tree and then descended the next tree with my bag and my suit and tie. And I thought I'd got away with it. But unfortunately, Terry Quinn happened to be standing out the meeting room and saw me come from an unexpected direction in the IPM and led to some questions. And so that was when I first met Terry, and he was very kind about it at the time. I was highly embarrassed, but there it was. Anyway, we're now going to enjoy a talk from Terry, and I invite Terry to make his presentation. Thank you, Terry.
Thank you, Peter. I'd forgotten that story, but the result was positive. I thought, that's a young man with initiative. So let me say what a great pleasure it is to be here. Not my first visit, as you know. I'm coming to talk to you about the story of units of measurement, meter convention and the BIPM. It's a fascinating story, but I'm going to start with one slide which sums up, in one sense, what it's all for, because although units are interesting, fascinating physics, it's for a purpose. So I thought I'd show you this slide here, which is something which I drew up with a colleague of mine last year. You know all this. In fact, most of you know all of what I'm going to say, but I'm saying it anyway. Metrology, the science of measurement, is part of the essential but largely hidden infrastructure of the modern world. We need it for high technology manufacturing, human health and safety, the protection of the environment, global climate studies, and the basic science that underpins all of these. Highly accurate measurements are no longer the preserve of the physical sciences and engineering. Many areas of chemistry, molecular biology, and medicine are now dependent on the ability to make accurate quantitative measurements. International trade in all manufactured and agricultural products are strictly controlled by regulations that need accurate metrology for their implementation. That's part of the background of what all this is about. I'm going to tell you a story. It begins on the 19th of March, 1791. Now, 19th of March is a special day for me, my birthday. Not 1791, I should say. I'm now going to show you two more slides, one from the middle of my talk and one almost from the end. From the middle of my talk, this one. Air France Concorde over the Atlantic at Mach 2.03, 18-kilometer altitude on the 7th of March 1999, en route for New York, photo TJQ. You might say, what is an international civil servant paid for by taxes of all the member states doing, sitting on Concorde? You might even ask, how is it that his wife was sitting behind talking to the captain while she was sipping a glass of champagne? There is an answer. I will come to that in the middle of my talk. Then, at the end of my almost my last slide, not quite my last slide, I will show you a draft of what is likely to be proposed to the 26th General Conference on Weights and Measures for a redefinition of the International System of Units. So let's go back to this report of the Academy of Science, dated 19th of March 1791, by some of the luminaries of French science in the 18th century: Borda, Lagrange, Laplace, Monge, and Condorcet. What do they say? The first paragraph: the idea of referring all measurements to a unit of length taken from nature was seized upon by mathematicians as soon as the existence of such a unit and the possibility of determining it became known. They saw it as the only way to exclude all that was arbitrary from a system of measurement and to conserve it unchanged, so that no event or revolution in the world could cast uncertainty upon it. They felt that with such a system, belonging exclusively to no nation, no one nation, one could hope that it would be adopted by all, sentiments with which we could completely agree. They then went on. They talked about this, and then we find, following page, one can reduce to 3 the units that seem most appropriate as the base: the length of a pendulum, the quarter of the length of the equator, and finally the length of a quarter of a meridian. The length of a pendulum has the advantage of being the easiest to determine and, in consequence, the easiest to verify if some accident happens that renders it necessary. Furthermore, those who wish to adopt this measure already adopted by another country, or having adopted it wish to verify it, would not be obliged to send observers to the place where it was originally established. In addition, the law of the length of the pendulum is well known, confirmed by experiment, and can be used without fearing small errors. I think we would agree completely with that. But as you know, this is not what they did. That was the first 2 pages of this report. By the time they got to page 16, they had turned the argument round and they had demonstrated quite conclusively that by far the best base of the unit of measurement would be 1/10,000,000th of the quadrant of the Earth passing through Paris. That's another story, another lecture which I will not go into. And they ended up with the metre and kilogram of the archives. This is the metre and this is the kilogram of the archives, which remains in the archives of France, and I was able to take it out a couple of years ago and actually photograph it. The metre was defined as the length of this platinum bar, which itself was estimated to be 1/10,000,000th of the quadrant of the Earth going through the Paris meridian. And as you can see, there are little marks at the end where over the years occasionally it has been used. It has not been used very much because almost as soon as it was made, it was put in the French archives. The kilogram has remained the cylinder of platinum iridium, a copy of which is here. And then the question arose afterwards, because shortening the story very much, All of this was adopted during the time of the French Revolution. People do not generally like to be told to change their units of measurement, and it was indeed many years before in France it was really adopted as a unit of measurement, the metre and the kilogram. After 1795, the question could be posed, what were the real definitions of the metre and the kilogram? We have the metre is 1/10,000,000th of the quarter of the terrestrial meridian, which deduced from the measurements of Metre and Delambre, the two famous people who did the triangulation. It was this 5,130,740 toises. Toise was the original unit of measurement in France. It was about this long, made up of 6 feet, feet of the king, the pied du roi. In each foot there were 12 inches. In each inches there were 12 lines. In each line there was 12 points. A point was a few tenths of a millimetre, quite precise. And they had measured the meridian in terms of this. So 1 metre was 443.296 lines of the toise. I say this because I come back in a moment. And the kilogram is the mass of 1 cubic decimetre of water at the temperature of melting ice. So was the definition of the metre 1/10,000,000th of the quadrant of the Earth, or was it the length of the metre of the archives? And this was never really decided. And the kilogram, was it the mass of 1 cubic decimetre of water, or was it the mass of the kilogram of the archives? Left a little bit vague. Who were the people who really needed to make accurate measurements of length in the first years of the 19th century? They weren't engineers in industry, because one didn't need to do that. Very precise measurements were made. Think of Harrison's clocks, remarkable pieces of engineering. But they did not rely at all upon any traceability to any unit of length. These things were adjusted to fit. The people who needed to make length measurements seriously were people who made maps, geodesy. And there was very great activity at the beginning of the 19th century in making maps of Europe, Central Europe. They continued to use their measurements based upon the old toise, the toise of Peru, because this was well established and various copies had been made at the end of the 18th century. And although the metre was introduced, the problem for geodesists was that the metre was not accessible, because the definition of the metre, whether 1/10,000,000th of the arc or the metre of the archives, was actually in the archives of France. And this was not a laboratory, it was a safe with a key. The copies that have been made for distribution, dissemination of the metre, were those in the Conservatoire National des Arts et Métiers, an institute in France set up at the time of the French Revolution that acted, in one sense, as a national laboratory. The geodesists were not very pleased with this. And at a meeting in October 1867, after a lot of discussion, they made a number of recommendations. I don't need to go into all of these, you can look at them on the screen. All very sensible, the sort of thing one might recommend today if you didn't have a basic standard of length accessible. But recommendation number 7 recommends the construction of a new European prototype of the metre to be based on the metre of the archives. Recommends the creation of a European International Bureau of Weights and Measures. Note, European International Bureau of Weights and Measures. The idea was that they would make a new unit of length that would not be an end standard. Now you remember the metre and the archives was a bar and the definition was the length, subject to damage and scratches. The idea was to use then modern technology, which was a line standard where you make 2 lines and the metre is defined as the distance between those 2 lines. This recommendation, and they recommended the delegates to bring these recommendations to the attention of their governments. Without going into history and politics, the 1860s was not a good time for relations between Paris and France, because Napoleon III and Prussia, Bismarck, were very much rivals for leadership of Europe. France was not invited to this meeting in 1867. So when this recommendation was produced, as you might imagine, alarm bells began to ring in Paris, because in Paris they considered themselves the owners of the metric system. So what happened? There were reactions in Paris from the Bureau de Longitude, the Académie des Sciences, and finally the French government. The Bureau de Longitude, this was another of those little institutions set up in France at the time of the Revolution. You remember in Great Britain there was the Longitude Committee, which in the end did not give Harrison the prize, but he developed his clocks. Something similar, the Bureau de Longitude, was created in Paris. Its statutes, among other things, were to improve the determination of longitude at sea and to retake the mastery of the sea from the English. This is what's written in the statutes. I was therefore particularly pleased about 5 years ago when I was elected a corresponding member of the Bureau de Longitude. As far as I know, I am the first British member of the Bureau de Longitude. And at the time, Great Britain had finally decided to scrap its last aircraft carrier. So I said to the members of the Bureau de Longitude, you have finally achieved one of your initial aims. The Academy of Science took all this very seriously, as did the French government. But there was a question from the Academy of Science of St. Petersburg. What is the definition of the metre? Two questions I put a few moments ago. The French government decided that it had to react, and it reacted by creating an international metre commission. Invitations were sent to all the countries with which France had diplomatic relations, inviting them to send delegates to a meeting of the French Commission. And the first meeting took place in August 1870. A particularly bad time to have a meeting, because that was right in the middle of the Franco-Prussian War, and Paris was under siege. It took place with a restricted number of delegates, but they set up a working group, and the working group then met, and the commission met formally in October 1872. And the great thing about these meetings was they were recorded almost verbatim. And so we have hundreds and hundreds of pages of reports of meetings of the Commission, and one can see what they talked about and what they decided. And I, having read all these, I can hardly criticize a single thing they said. They were people like us. They were high scientists. Most of them who came were members of their local academies of science, and they had to decide, how are we going to make a better metre standard and a better kilogram standard? In the end, they came to a conclusion that indeed one must set up an international bureau, not a European Bureau of Standards, but an international Bureau of Weights and Measures. And the diplomatic conference of the Metre was held in Paris from the 1st of March to the 20th of May, 1875. I just show you these pictures because, as you know, nothing ever happens without people. Metre, who lived 1783 to 1875, he was the first president of the International Metre Commission. Dumas, he was a French chemist who was the president of the diplomatic conference. And then two people, Adolf Helsch and Wilhelm Förster, these were the two drivers for the creation of the Metre Convention and the BIPM. Hirsch was the director of the observatory in Neuchâtel, and Förster was the director of the Berlin Observatory. Arthur Morin was the director of the Conservatoire National des Arts et Métiers, who himself wanted to be the place where the new metre was made. Tesker was his assistant, and Saint-Clair de Ville, he was the famous French chemist who finally knew how to make platinum iridium alloys. I show you that because it's important to emphasize that these things happen because people do it. That nothing happens, a committee does nothing, it's the people who do things. The Metre Convention. This was the first convention that set up an international scientific institute. I don't need to read all of this, but this is the way it looks. First of all, the list of the names of all the heads of state. There were 17, starting with the Emperor of Germany. Then they said, wishing to assure the international unification and the improvement of the metric system, have resolved to conclude a convention to this effect and have named the following plenipotentiaries. Then the list of all the people who took part in this. Then they said, who having presented their credentials found to be in good order and due form, have decided upon the following arrangements. First article, the high contracting parties undertake to create and maintain at their common expense an International Bureau of Weights and Measures with its seat in Paris. Article 2, it's all about where it's going to be and so on. Article 3, the International Bureau shall operate under the exclusive direction and supervision of an International Committee for Weights and Measures, itself placed under the authority of a General Conference on Weights and Measures, formed of the delegates of all contracting governments. Why should it be interesting that I read you this text of a treaty that was signed in 1875? The answer is because that treaty is still the treaty that governs international relations in terms of metrology. It's quite remarkable. It is the only one that has lasted so long. Having decided that, this is essentially the structure of what was created. Metre Convention, General Conference, International Committee, International Bureau of Weights and Measures. It had to go somewhere. So the French government, having just come through the 1870 Franco-Prussian War, very generously offered a site to the International Committee, the old Pavillon de Breteuil in the Parc de Saint-Cloud, with the words, you can take it and demolish it, or you can repair it. I'm glad to say it was repaired. This is a photo taken in the 1920s. They made a laboratory, a quite remarkable laboratory, based upon ideas from Förster. And this laboratory still exists. You can see it. These were big rooms, 5 meters dimensions roughly, with the specific idea that they should be large so that the introduction of an observer would not change the average temperature very much. They had put, I want to show you, they had put air conditioning, they had zinc panels on the walls where they originally had temperature control air, then they had to put temperature controlled water because air was not sufficiently, not enough calorific value. And the problem was, in those days, it was almost impossible to make big zinc panels with cold water flowing through them that did not leak. And the reports of what went on in the laboratories at the time showed it was a very unhealthy place in which to work. And in fact, the second director of the laboratory died of pneumonia, almost certainly caught in working in the laboratories. It's not quite like that now. So they made beautiful laboratories. They made beautiful instruments to put in them. And the photograph of the balance room, this is not 1875. This is rather later, probably in the 1930s or 1940s. I can't quite judge from the style of the suit, but men's suits didn't change all that much. But you see the way it was that the operator was a long way away from the balance to avoid thermal influence. It all worked. They made the international prototype of the kilogram and the metre, and they put them in a safe. The kilogram was kept in its triple cloche. There were copies. The metre was in a cylinder, supported a bit like this. All of this is very well known. And the building was made to look a bit better. These were photographs taken recently. These are the laboratories. And this is the site as it is now. It has been expanded very considerably. This is the original Pavillon de Breteuil. This is the first laboratory you saw. It was extended in 1929. This was the servants' quarters. This building was built originally in 1672 by Louis XIV for his brother, who lived in the Château de Saint-Cloud that was at the end of that line there. Maybe appropriately, the director of the BIPM lives here, and the deputy director lives in the servants' quarters. I should say, I have to make a small correction, Peter. When I joined in 1978, I joined as deputy director. I became director in 1988, so I moved from the servants' quarters to the big house. The International Committee for Weights and Measures originally met once every 2 years, and they met for 2 weeks because, of course, travel from around the world wasn't as easy as it is now. I don't need to go through the names of all of these people. At that time, of course, Australia was not an independent country in the sense it could sign the Metre Convention. This came later. 100 years later, the International Committee still meets on the steps of the same building, and this photograph is interesting for 2 reasons. It is exactly 100 years after the previous one, and it is the first photograph where we have a woman member of the International Committee, Catherine Gebbie, who at the time was head of the physics division at the National Institute of Standards and Technology. You might recognize the face there. Bill Blevin, at the time, was director of the lab here. The first General Conference we have no photograph of. This is a photograph of the second General Conference in 1895, taken sitting in the courtyard of the International Bureau. That's the introduction. Then, having got to the stage where we have a new metre, a new kilogram, what happened next? James Clerk Maxwell, in an address to the physics division of the British Association for the Advancement of Science in Liverpool in 1870, said some interesting things. I'll read the whole of this because although I've outlined part of it, that's part which is well known. The first bit is interesting. This subject, and he's talking about measurement, is one in which we, as a scientific body, we being the British Association, take a warm interest. And you're all aware of the vast amount of scientific work which has been expended and profitably expended in providing weights and measures for commercial and scientific purposes. The Earth has been measured as a basis for permanent standard of length, and every property of metals has been investigated to guard against any alteration of the material standards when made. To weigh or measure anything with modern accuracy requires a course of experiment and calculation in which almost every branch of physics and mathematics is brought into requisition. I think we would say the same thing today. If you look at the National Metrology Institutes, this is exactly what they're doing. He then went on, yet after all, the dimensions of our Earth and its time of rotation, though relative to our present means of comparison very permanent, are not so by any physical necessity. The Earth might contract by cooling, or it might be enlarged by a layer of meteorites falling on it, or its rate of revolution might slowly slacken, and yet it would continue to be as much a planet as before. But a molecule, say of hydrogen, if either its mass or its time of vibration were to be altered in the least, would no longer be a molecule of hydrogen. If then we wish to obtain standards of length, time and mass, which shall be absolutely permanent, we must seek them not in the dimensions or the motion or the mass of our planets, but in the wavelength, the period of vibration, and the absolute mass of these imperishable and unalterable and perfectly similar molecules. This is the development of the idea that the great thinkers of the 18th century had. They didn't talk in these terms, but this is what they were aiming at. But of course, at that time, it was not possible to implement Maxwell's precepts because we didn't have the science. Yet the International Committee of Weights and Measures was very conscious of this. This is an extract from the 1891 meeting of the International Committee. From the very beginning of the International Committee, it has been generally recognized to be of fundamental importance to determine the relation between the metric units and some basic fundamental constants that one can deduce from natural phenomena. Of course, following upon Maxwell, following upon the old people. What did they do? They invited A.A. Michelson to come to BIPM with an interferometer and measure the wavelength of light in terms of the new international meter, the red line of cadmium, which he used. And he did. He worked with Benoit, who was the first director, and they obtained a result. You don't need to bother about the details of this. I'll just say that the result obtained by Michelson was very close to a much improved one made in 1906 by the director of the BIPM, Benoit, and Fabry, or the famous Fabry-Perot interferometer, who found a very similar number from which they could deduce the wavelength of light. This same value was taken by the 7th General Conference in 1927 to define the angstrom. And then in 1960, when finally the definition of the meter was changed from the length of a platinum iridium bar to the wavelength, a certain number of wavelengths of the light of krypton, they took the value that was consistent with the value of the angstrom and that was consistent with the value of Michelson in the end of the 19th century. One might ask the question, why did they wait so long? One could say, well, the International Committee was very conservative. It was, but not to that extent. It was quite reasonable because when they were doing these measurements, Benoit and Fabry, they realized that the width of the spectral lines they were using were not as thin as they should be. At that time, they were not aware of the existence of isotopes. It was only in the second decade of the 20th century when the physics began to be understood that they realized this. And at the same time, the accuracy with which they could do mechanical length measurements was quite remarkable. They could make comparisons of length measurements to a tenth of a micrometer. So there was no pressing need to do it. And it was only after the Second World War, when samples of monoisotopic krypton, for example, became available, that they really started to do it. So there was reason behind this. But this was the first move away from mechanical standards. I don't go into the details of the other units because I want to move on. The second were based upon Earth rotation, then the rotation of the Earth around the Sun, and that's another story because the way in which that was done leaves us with the leap second, which was unfortunately, in my view, a mistake by the astronomers, but that's yet another talk I can give you sometime. Kelvin, candela, mole, ampere, but we're still left with the kilogram. National Metrology Institutes were created, the PTR 1887, NPL 1900, NBS 1901, and of course National Standard Laboratory Sydney 1938. I said 19th of March was an important date for me. 1938 was also an important date because I'm the same age as the NSL. Then we come to how do we know that measurements made by many NMIs are consistent with each other? How do we know they're accurate, and who cares? And we test their mutual consistency by international comparisons. And since 1999, these have been carried out under a scheme set under the auspices of the International Committee for Weights and Measures called the CIPM MRA. And this is where I make a little divergence before I come back to units. The mutual recognition arrangement, of which all those people here who work in international metrology be well aware, it's a scheme set up to formally demonstrate the equivalence of measurement standards. The essential points are to establish the degree of equivalence of national measurement standards maintained by NMIs, to provide the mutual recognition of calibration and measurement certificates, thereby to provide governments and other parties with a secure technical foundation for wider agreements related to international trade, commerce, and regulatory affairs. And the process, international comparisons, supplementary comparisons, and quality systems and demonstrations of competence by NMIs. Those few words, demonstrations of competence of NMIs, are words that took an enormous amount of effort to obtain agreement on. And the engagement is directors of NMIs sign the MRA with the approval of the appropriate authorities in their own country and thereby accept the process, recognize the results of key and supplementary comparisons, and recognize the calibration and measurement capabilities of other participating NMIs, as in the BIPM database, where all this appears. This was signed in 1999 at a meeting that took place at the Collège de France in October. You will see that it was signed by our dear friend Barry on behalf of NML CSIR Australia. It was also signed, of course, by Karen Brown on behalf of NIST United States. That's where my trip on Concorde comes. On the 7th of March 1999, having travelled enormously to persuade directors to set this up, some of those travels were accompanied by Bill Bevin, at that point Secretary of the CIPM, and helping me very much with this, because the question of mutual recognition and demonstration of competence, it was difficult for some laboratories to accept that they would have to submit to peer review. And it was only at the very end I was able to do this. In so doing, going round to all these directors, I accrued an astronomical number of air miles. And in fact, I was travelling on Concorde, not at the taxpayer's expense, but Air France expense, because they offered myself and my wife a free weekend trip to New York on Concorde. So I took this and made a side trip to Washington. And it was at that point that I was able to persuade Karen Brown to accept this. So there you are. Who cares? A lot of people care. At the 10th anniversary of the signing of the CIPM MRA, we had a meeting in Paris, and we had a vice president of Boeing. He said, Boeing has recently been one of the first industrial corporations to take advantage of the CIPM MRA. Boeing utilizes the CIPM MRA equivalence data to support our global measurement system. We rely on the peer-reviewed NMI capabilities to support our emerging technologies. If there are any companies in Australia that subcontract to Boeing, you can be sure that Boeing has taken note of the fact that these companies are linked with their standards to NMIA. If they were not, then those companies would have to go to NIST to get their calibration certificates. And this is one of the reasons. This helps everybody, it helps the companies, and it helps the National Metrology Institutes. This is why it's important, and this is why we have to continue doing it. Back to units. As far as the unit of in 1971, the then Secretary of the International Committee, Jan de Boer, made the following remarks. This was the conference where the new unit of the mole was introduced. And he was thinking about other units. As far as the unit of mass is concerned, the choice of an atomic definition, for example, the mass of a proton or the unified atomic mass unit would seem natural. But such a proposal seems to me still a far cry from practical because of the necessity of determining to high precision the mass of a proton, not possible in 1971. As regards electrical units, here again one could imagine the elementary charge of the proton as the natural and fundamental electrical unit to serve as the base of a universal system of units. But in this case as well, it is the requirement of metrology that renders such propositions impracticable for the high precision measurements of electrical quantities. Not yet possible. And he ended by saying, naturally, one might ask also in the case of the mole, would it not be preferable to replace the definition of the mole, given here by a molecular one, but as in the case of the units of mass and of electrical current, this would require determinations such as the absolute counting of molecules or the measurement of the mass of molecules that are not possible with the required precision. So, despite what was said by Maxwell in 1870, in 1971, 100 years later, it was still not technically possible to do this. What changed it all? What changed it all was the key discovery in physics that opened the way to a transformation in the way the base units of the SI are defined, in the way suggested by Jan de Boer, and I would add Maxwell, and going back to the savant of the 18th century. It came only a few months after he made these remarks. It shows the unpredictability of science. This was the quantum Hall effect discovered by Klaus von Klitzing in 1980, in which a macroscopic electrical resistance can be developed that is exactly proportional to h upon E squared. H is the Planck constant, E is the charge on the electron, or the proton if you prefer. This, together with the Josephson effect discovered in 1960, which allowed a macroscopic voltage to be developed exactly proportional to 2E upon H, opened the way to producing an electrical power exactly proportional to a combination of fundamental constants, and that is what changed everything. Two ways then became possible to link mass to fundamental constants. The first is by means of a Watt balance, which I will perhaps not describe in detail to you, in which an electrical power is compared with a mechanical power to give a value for the H, the Planck constant. And the second is via measurements of the crystal density of silicon, which gives a value of the Avogadro constant, which is linked to H through this equation here, which includes other constants, the fine structure constant, the Rydberg, the molar mass constant, and the relative atomic mass of the electron, which are all known very precisely. So we have two ways of measuring the Planck constant. I won't go through this because you know all this. I don't need to go through it. But what I will do, I will just tell you why it is important that you measure the Planck constant by two different methods before you start to use it to define a unit. Silicon crystal density, we have the Avogadro constant is small n, the number of atoms in a unit cell, which is 8, the molar mass divided by the density of a sample and the lattice spacing, where n is the number of atoms per unit cell, etc. So you can write down from the equation on the previous slide that the silicon, if you like, value of H is given by this relation here, which is based upon mechanical measurements and fundamental constants. The Watt balance value of the Planck constant is given by a mass, little g, a velocity, and two integers and a frequency, which can be measured to high accuracy. The fact that with Watt balances and by measuring crystal density of silicon, you obtain a value of the Planck constant within a few parts of 10 to the 8 on one hand is quite remarkable. What does it demonstrate? The most important outcome is the demonstration that the Josephson and quantum Hall relations correctly represent macroscopic voltages and resistance, something that had not been demonstrated at this level before, because the physics of the silicon crystal density is completely different from the physics of the Watt balance and the physics of the quantum Hall and Josephson. It also demonstrates a remarkable level of consistency among the measured values of the fundamental constants, using a wide variety of methods based on equally wide variety of equations of physics. And one can deduce that classical and quantum physics in these areas are consistent to a few parts in 10 to the 8. And this is a really important result. On a much more practical level, this agreement has opened the way to redefine the kilogram. By fixing the numerical value of H, the kilogram can be realized by methods based on either of these two equations with an accuracy sufficient for all practical needs. And this is the key to the new SI. let me just say a word. What does it mean to fix a numerical value of a fundamental constant? One might say the value of a fundamental constant is a constant of nature. It's not up to us to fix its value. Be careful. We have to distinguish between the numerical value and the value. Here we have the value of h is this number here, kilogram, meter squared, second to the minus 1. Value of h, numerical value times the units. The value of h is a constant of nature. If we define, as we do now, the 3 units, kilogram, meter, second, independently, then we must determine the numerical value of h by experiment. And we have these 2 experiments, you remember. And it will have an uncertainty. That is the present situation. And this is what we're doing with watt balances and silicon crystals. However, if the meter and the second remain independently defined, we choose to fix the numerical value of h, then the effect is to define the kilogram, define the size of the kilogram. This is the proposed new definition of the kilogram. The numerical value will have 0 uncertainty. We just have to make sure that we choose the right value of h, i.e. one that is really consistent with the present definition of the kilogram. This is why we do it in 2 independent ways. In the same way as for the speed of light, since 1983, where the meter was defined in terms of a fixed value of the speed of light, once the numerical value of h is fixed, it will no longer be susceptible to measurement. Experiments that previously measured h will become realizations of the kilogram. That's the key essential point of what we're doing in our proposed new definition of the kilogram. Why do we need to do it? I've got this, I have to make this little demonstration for you. The reason we need to, this is not the real one. Doesn't seem to weigh a kilogram to me. The reason we need to define a definition of the kilogram based upon something which is unchanging is because if we drop it, if we drop the kilogram, it'll change. But by definition at the moment, its mass will be 1 kilogram, and therefore if we do in fact drop it on the floor, its mass will not change, the mass of the rest of the universe will change. And that is not a very satisfactory situation. So we have to do something about this. And this is why we are proceeding to a redefinition, having opened the door by being able to redefine the kilogram. And so what we're proposing, and this has been through lots of discussion, and what I'm showing you now may not be the final text, but these are the texts as they are now going towards our final decision by the CIPM and then in due course the General Conference. The 26th CGPM, considering that the essential requirement for an international system of units is that it be uniform and accessible worldwide for international trade, high technology manufacturing, human health and safety, protection of the environment, global climate studies, and the basic science that underpins all of these. That the SI must be based on our present theoretical description of nature at the highest level, and that SI units must be stable in the long term and internally self-consistent and practically realizable. That a revision of the SI to meet these requirements was described in Resolution 1 of the 24th CGPM in 2011, where the principle of this was adopted. Laid out in detail a new way of defining the SI based on a set of 7 defining constants drawn from the fundamental constants of physics and other constants of nature, from which the definitions of the 7 base units are deduced. That the conditions set in 1911 have been met, decides that henceforth the International System of Units, the SI, is a system of units in which, and then we lift the 7 defining constants with their numerical values that will be fixed. Then, Appendix 1 of the Resolution, the base units of the SI. It follows from the new definition of the SI adopted above in terms of the 7 defining constants that the base units of the SI are henceforth defined as follows. Again, these may not be the final ones, but they're close to it. The second, the symbol S, is the SI unit of time. It is defined by taking the fixed numerical value of the cesium frequency, delta nu Cs, the unperturbed ground state hyperfine splitting frequency of the cesium-133 atom, to be 919263170 when expressed in the unit Hertz, which is equal to second minus 1 for periodic phenomenon. We're changing the wording of that definition, we're not changing its substance. The meter, symbol M, is the SI unit of length. It is defined by taking the fixed numerical value of the speed of light in vacuum to be 299792458 when expressed in the units metre per second, where the second is defined in terms of the Cesium frequency of delta nu Cs. The kilogram, this is the one that really is changing, one of the ones that's changing. The kilogram, symbol kg, is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant to be that when expressed in the unit joule second, which is equal to kilogram metre second to the minus 1, where the metre and the second are defined in terms of c, speed of light, and delta nu s. And the ampere, symbol A, big change again, the SI unit of electric current, it is defined by taking the fixed numerical value of the elementary charge to be that when expressed in the unit coulomb, which is equal to ampere seconds, where the second is defined in terms of the delta nu. And then the last, the Kelvin, symbol K, is the SI unit of thermodynamic temperature. It is defined by taking the fixed numerical value of the Boltzmann constant to be that when expressed in the unit joule per Kelvin, which is equal to kilogram metre squared second to the minus 2 Kelvin to the minus 1, where the kilogram metre second are defined in terms of H, C, and delta nu C. The mole, symbol M, but symbol mole, is the SI unit of amount of substance of a specified elementary entity, which may be an atom, molecule, ion, electron, or any other particle, a specified group of particles, defined by taking the fixed numerical value of the Avogadro constant to be that when expressed in the unit mole. And finally, the candela, symbol CD, is the SI unit of luminous intensity in a given direction. It is defined by taking the fixed numerical value of the luminous efficacy of monochromatic radiation of this frequency, KCD, to be 683 when expressed in the unit lumen per watt, which is equal to candela steradian per watt, or kilogram minus 1 metre squared second cube candela steradian, where the kilogram metre second are defined in terms of HC and delta nu Cs. That is the sort of thing that's going to be proposed. It's complicated, and it's complicated for a good reason. Let me just tell you why it's complicated in a completely different way. I showed you earlier the photograph of the safe in which you had the kilogram under its cloche and you had the metre in the thing above it. I remember when I was young, our telephone at home was a Bakelite cylinder with a speaking and took the earpiece and you dialed the number. I would say that the metre and kilogram, as they were in the safe, that's simple science, easy metrology to understand. The telephone, at that time, it was simple science, easy to understand. I could unscrew it all. I could see the diaphragm, I could see the coils, and I could see the wire going off to the exchange. Today, we have a new definition of the kilogram. It's high science, more difficult to understand, but it's precise and rigorous. Today's telephone, an iPhone, who knows how it works? No one knows how it works. But you don't say, it's no good, I can't understand it, it's of no use to me. One has to say these days that science has advanced, metrology has advanced, and the fact that our definitions of units now include high science means that they are more difficult to understand than they were in the old days, in exactly the same way that iPhones are more difficult to understand than old-fashioned telephones. That's the sort of argument I give. One final point, I'm slightly overrun. I quoted Jan de Boer, 1971, talking about definitions that were not realizable at the time. He said, well, we could envisage a unit of mass based upon the mass of atoms. Indeed, one could. And you could have seen that we have these two ways of measuring the Planck constant. One of them involves measuring the Avogadro constant by means of silicon spheres. One could say, well, why don't we take the mass of a silicon atom as a definition based upon a definition based upon the mass of an atom of silicon, which we could do. A very good reason not to do that is that by fixing the Planck constant and the charge on the electron, the Planck constant for the kilogram, we have fixed values for the Josephson constant and the von Klitzing constant. And these are used in practical metrology for reference standards of the volt and the ohm. And these are already used at the level of parts in 10 to the 10, and even more precisely than that. I saw in a paper recently comparing the von Klitzing constant measured with graphene and with silicon arsenide. Differences were parts in 10 to the 11. Electrical metrology can benefit from having fixed values of the quantum Hall and Josephson. And in the practical realizations, having fixed H and E, there will be no limit to the accuracy with which the electrical standards can be realized in terms of SI units. And in terms of mass, we don't need to go to parts in 10 to the 10, parts in 10 to the 11. And therefore, had we fixed it on terms of a mass of an atom, we would have lost the possibility of fixing both H and E. These are the sort of discussions that have taken place, and the conclusion is that we now all agree it is the Planck constant and the charge on the electron because of this use in electrical metrology. Excuse me, I've been talking a little bit too long. One or two more quick slides to show you. I don't need to go into this. I don't need to go into that. Silicon spheres. Silicon spheres are actually beautiful things to see because they are, I think I'm right in saying, people say they are the most spherical objects in the universe. They're spherical to tens of nanometers. Do you remember the photograph of the kilogram in its safe? This is the equivalent. At the BIPM, they have set up a set of reference standards, not as the definition of the kilogram, but for the purposes of international comparisons and reference standards. This is what a watt balance looks like, big one. That's the one at NRC. This is an enormous one made by NIST. Silicon spheres on a balance. That's a watt balance I made in my basement. Now, it has a purpose, this, because although I said that the modern definition, the new definition of the kilogram is high science, it's high science, but it's understandable. And with Richard Davis and my 11-and-a-half-year-old grandson, who made the Lego bits, we made a watt balance that precisely follows the definition, and we were able to measure the mass of this object without calibrating the balance, only from electrical units, which were based, this is in the BIPM, and therefore they were based upon their quantum Hall and Josephson. And we exhibited this at the Royal Society's Summer Science Exhibition in 2013, and we had a silicon sphere, and we were able to explain to high school students what we were planning. And they're very smart, these kids. They understood it. And they could see that, although the practical realization here is simple, they could see that you could do it very much better than that. I should say that NIST, when they saw this, they said, we can do better. And they made a Lego watt balance, which is indeed only 5 times better. This worked to about 5%. They say they can do it to 1%. And we published it. I'm very proud of this because this is a scientific paper. Terry Quinn, Lucas Quinn, and Richard Davis. Lucas Quinn, age 11 years. Okay, and that's the end of my story. I've slightly overrun. Thank you very much.